Albert Einstein forever changed our views of the universe with the theory of relativity. He turned physics on its ear yet again when he published a paper on the photoelectric effect. It required the particle nature of light and a new particle called the photon. What new information can we get from measuring light as a particle instead of a wave? We'll discuss this next. Stay tuned. Light was happily thought to be a wave. Then it was discovered that when you shoot light at a sheet of metal, the metal emits electrons, particles that are electrically charged. This is called the photoelectric effect. It could be explained by light being a particle, referred to as the photon. Einstein won his only Nobel Prize for this discovery. CCD cameras, like those in cell phones, work on the particle nature of light. The energy of a photon is given by the following equation. E is equal to h times frequency, h being a constant. In simplified form, we see that energy is proportional to the inverse of the wavelength. This simple relationship tells us that smaller wavelengths produce higher energy. Adding this to our earlier relationship, bluer light equals higher energy, and redder light equals lower energy. Another surprising behavior of light will require a bit of background on the structure of the atom. Each atom contains a nucleus with some number of protons, with positive charge, and neutrons, with no charge. The nucleus is surrounded by electrons with negative charge that occupy one or more orbitals. The orbitals are at precise distances from the nucleus and are specific to each atom. In a crude analogy, think of the planets in our solar system. Each planet occupies an orbital. Electrons can change orbitals. If an electron gains energy by absorbing a photon, it can jump to a higher orbital. If an electron emits energy, it can fall to a lower orbital. The amount of energy is very precise. Any more or less than that required will not change the electron's orbital. This is called a quantum leap.
When an atom was heated, its electrons would become agitated and leap from one fixed orbit to another. Each downward leap would emit energy in the form of light in very specific wavelengths. And that's why atoms produce very specific colors. This is where we get the phrase quantum leap.
If it weren't for the quantum leap, you would have this smear of color coming out from an atom as it got excited or de-excited. But that's not what we see in the laboratory. You see very sharp reds and very sharp greens. It's the quantum leap that's the origin and the author of that sharp color.
What made the quantum leap so surprising was that the electron goes directly from here to there, seemingly without moving through the space in between. It was as if Mars suddenly popped from its own orbit out to Jupiter.
Electron positions in an atom, we call energy states, are like books in a bookshelf. You can find books on one shelf or another, but not in between. This behavior produces the states described by Kirchhoff's laws. A hot, glowing solid is an example of an emitter. The glowing solid will produce a full spectrum, referred to as a continuous spectrum. In other words, the full rainbow. Though continuous, not all colors will be the same intensity. More to come on this in a moment. If a cool, diffuse gas lies between the observer and the emitter, an absorption spectrum will result. The gas has absorbed light and removed it from the spectrum. Black bands will appear in the continuous spectrum. A hot, diffuse gas will produce an emission spectrum. Here we have lines of color instead of dark lines. Emission lines can be across the entire range of visible wavelengths. Pictured here is the combination of all possible spectra defined by Kirchhoff's laws. Relating this back to our energy states, if a ground state atom absorbs energy, the electron will jump to a higher orbital, or an excited state. If that electron then falls back to a lower state, the electron gives off a photon that is observed as emission. Spectra is a very powerful tool. Every element has its own unique characteristic spectral lines. Therefore, we can easily determine the composition of an object by its spectral lines. Here is the sun's spectra. It's obviously very complicated. However, from the spectra, we know the sun contains the following elements: hydrogen being the most common, followed by helium. But wait, this is an absorption spectra. That means, according to Kirchhoff's laws, the sun is a glowing solid surrounded by a cool gas. How can the sun be thought of as a cool gas? Let's return to our glowing solid. Kirchhoff's laws specified the glowing solid to be a black body. This is a special object that behaves as a perfect absorber, in other words, an object that absorbs all incoming radiation, and a perfect emitter. That means it re-radiates all radiation that falls on it at a wavelength based upon the object's temperature. All objects in space, believe it or not, including planets and stars, behave as black bodies, strange though that may seem. We are already somewhat familiar with this concept. We know that a whiter metal is hotter than a redder one. We previously mentioned that a glowing solid, in other words, black bodies, radiate at different intensities. This image shows various black body curves. All black bodies of the same temperature have the same curve. The peak of the curve is a special value called lambda max. If you know lambda max, you can calculate the temperature of the object using Wien's law. This is powerful. Since all black bodies have the same curve for a given temperature, you just need a few points on the curve to find the object's temperature. The curve is easy to get using a method called photometry. Using this simplified version of the equation, we can see that the lower the temperature of an object, the longer lambda max. As an example, we can determine the temperature of the sun by measuring lambda max to be 500 nanometers. Plugging and chugging, as we call it, produces the result of 5800 Kelvin. Notice the sun peaks in the visible part of the spectrum. Here we see the black body curves of objects of various temperatures. Notice the peak is not always in the visible range. Very hot stars, with temperatures around 60,000 Kelvin, peak in the ultraviolet. They would be brighter in the ultraviolet than they would in visible light. Cold objects, like a 600 Kelvin newly forming star, never appear in the visible at all. One more useful relationship for black bodies relates energy to temperature. The equation E is equal to sigma times T to the fourth power, where sigma is a constant. Again, using the simplified version helps us see that even a little temperature increase leads to a huge difference in energy. The energy of a blue star is much greater than that of a cool red star. We can see that doubling the temperature leads to a 16-fold increase in energy. This dramatic increase is why cool objects glow red, while hot objects are blue. Finally, here is a summary of all of our relationships between wavelength, temperature, and energy. We also know that light can be reflected. We see the moon because it reflects sunlight. Mars is red because it absorbs all but the red light. This gives us clues to the makeup of an object too far away to see as a disk, like the bluish color of Neptune, for example. Note that reflected light is not the same as black body radiation. Reflected light is not an indicator of object temperature. Light can also be scattered. Particles tend to scatter radiation with a wavelength of a similar size to the particle. The red sunrise and sunsets on Earth are clues to the size of the particles in our atmosphere. As an interesting note, Earth, the blue planet, has a red sunset, while Mars, the red planet, has a blue sunset. Light is one of the most powerful and useful tools in astronomy. Thank goodness, since it's all we have for many objects.
This is the testing room for my very latest and greatest invention, television chocolate. One day it occurred to me, hey, if television can break up a photograph into millions and millions of tiny little pieces and send it whizzing through the air, then reassemble it on the other end, why can't I do the same thing with chocolate? Why can't I send a real bar of chocolate through the television all ready to be eaten?
I'm not gonna touch it. I'm not going in that direction.
Sounds impossible.
It is impossible. You don't understand anything about science. First off, there's a difference between waves and particles. Duh! Second, the amount of power it would take to convert energy in matter would be like 9 atomic bombs.
Mumbler! Seriously, I cannot understand a single word you're saying.